is the condition for matrix multiplication? When do we say that we can perform a matrix multiplication or not? Can you tell me what is the prerequisite? Anyone, what is the prerequisite for matrix multiplication?
हम एक का width एक का like width एक दूसरे का height के बराबर होना चाहिए.
Rows of one should be equal to the columns of second, right? Columns of one should be equivalent to the rows of the other. Only then we can say that we can perform matrix multiplication, otherwise we cannot perform. So this is the prerequisite, right? So we say that here, so we will be considering that the matrix that we are going to consider over, they are already compatible. That means they are eligible for the multiplication. Now what we are going to see in matrix chain multiplication, what we are looking forward is that we are not actually going for, we are trying to understand that we are not talking about the output, the result of multiplication. We are talking about that in what order the multiplication should be performed so that we are able to minimize the cost of multiplication. So that means the number of multiplications that are required to be performed, right? So the questions, then we say, how is it possible that if there are two matrices, we require the same number of multiplications? Yes, for two matrices, that we require only the same number of multiplications. But when we have large number of matrices, let us say we have three matrices and we want to multiply. So what should we do? Whether we, let us say we have three matrices A, B and C, and now we have to multiply. So whether we should multiply A and B first, and then the result of A and B should be multiplied with the C, or we should multiply B and C first, then we should multiply the result of B and C with A. Then the third case is we should multiply A and C first and then multiply the result of A and C with B. So what is the, are we going to get the same cost for doing all these kind of multiplication? No, the cost of multiplications vary with the parenthesis. So that means parenthesis, we say if I'm going to multiply which one first. If something is there in the parenthesis, that is evaluated first, and the outside one is evaluated later. So we say we are going to understand the concept of parenthesis. So the which two matrices should be parenthesized first so that we are able to reduce the cost of multiplication. So the problem statement says, given a sequence of matrices, find the most efficient way to multiply these matrices. The problem is to decide the sequence of the matrix multiplications. That's what I said. What should be the sequence? Either it should be ABC or CBA or BAC. So you can imagine the number of sequences that can be generated using these three matrices. So you can say this is a optimization problem, because what we are going to do is our objective is to minimize the cost of multiplication. So how can we minimize the cost of multiplication? So we are saying, can we perform the least by performing the least number of multiplications? So let us understand how many. First of all, we should understand how many multiplications are required. So here you say we have two matrices. One is of the order of 2 by 3, they are the dimensions, and second matrix B is of the order of 3 by 2. So when we multiply this, if you simply write the matrix multiplication, you count the number, you see the count. We say 2 into 1, 3 into 3, 1 into 5 plus 3 multiplication. Similarly, 3 plus 3 is 6, plus 3 9, plus 3 10. So rather than doing this, can we compute this number of multiplications? We can see it from the dimensions only. From the dimensions, we say that dimension 3 by 2. Since 3 and 3, first matrix is having 3 columns and the second matrix is having 3 rows. So this is common. So we are going to take just one of these. So we say 2 multiplied by 3 multiplied by 2, that gives us the total number of multiplications which are required for getting the solution for this particular matrix, that is C2 by 2. So the total number of multiplications which are required is 12. So this is the cost of multiplication when we have two matrices of the order of 2 by 3 and the order of 3 by 2. So just looking at the dimension of the two matrices, you can tell what is the cost of multiplication of these two matrices. You need not perform the computations. So now let us take another example. So where we have the four matrices. So can you tell me how many possibilities are there in order to, you can see how many possible sequences are there for multiplying these matrices. So the possible sequences we have to generate in such a way, because we have to see that we can perform the matrix multiplication only when the rows of one matrix are equivalent to the columns of the another matrix. So only then we can perform the. So considering these factors, the eligibility criteria, there are five possible ways with the help of which we can perform the matrix multiplication using the four matrices. So here you can see all these five possibilities have been created over here. Since the matrix multiplication is associated, so they are going to, although see the output will be same, but the cost of multiplication varies. So that means if the output is same, why can't we have, why shouldn't we go for the matrix multiplication method, which gives us which requires least amount of time, right? So that will be able to reduce the complexity of the task. So here you can say whether we should A cross B cross C cross D, then A cross B cross C cross D. So this is how you can say, looking at the parentheses, you can understand which two multiplications are performed first, then we compute the next multiplication with the result of the previous multiplication. So from these, you can say this is called as a sequence of matrix multiplication, and this is associative. Now the question is, out of these five combinations that we can see, the out of five sequences, which one is the best? Which one is going to give us the minimum number of multiplications? Which one is going to help us in minimizing the cost of multiplication? So let us do with the help of example. So here we see we have taken three matrices A, B, and C. So let us say we multiply A, B first, and then we multiply it with the C. So this will require 40 into 20 into 60. So 4, 6, 24 into 48. That means 408. 400. Sorry, 48,000. Then plus. See the result of this. The result of this will be 40 by 60. The dimension I'm saying, let us say A cross B, when we multiply, we get a new matrix M. Its dimension will be 40 by 60, right? So 40 by 60 into C 60 by 50. So that will give us 40 into 60 into 50. So that is being done over here. So we will see the dimensions. So when we add this is equal to this number of multiplications. Similarly, if we do the other way, so we are multiplying the B and C first, and then the output of B and C will be multiplied with the matrix A. So 20 into 60 into 50. This is the dimension. This is how we find out the number of multiplications required. So this will this is going to give us 2 5s 10 into 6 12,000. Sorry, 2 5. Yes, right. So when we perform this computation, after that, see 40 into this requires, so B 20 by 60 and B 60 by 50. The output of this dimension will be a new matrix that will be of the order of 20 by 60 by 50. So the output matrix will be 20 by 50 by 60, and the previous matrix was 40 by 20. So from there we can compute the new values that are going to come up is equivalent to this is 40,000 plus 60,000, and this is equal to 1 lakh multiplications. So from here we can see that which one of these, both of these are requiring, one is require 1,68,000 multiplication, and 68,000 multiplications are reduced if we are applying the second way of performing the multiplication. So this is how you can see, from here we can see the minimum number of multiplications are required. And then see, this is one example. Now see another example, A 10 by 100, A B 100 by 5, C 5 by 50. So from here again, if we see, there is a difference of 75,000 and 7,500, right? So that makes a big difference when we are multiplying the matrices. So the cost of matrix multiplication is basically the scalar multiplication. The order of these parentheses requires different number of scalar multiplications, as we can see. So since it requires different types of scalar multiplications with the change in the parentheses. So can we devise some mechanism with the help of which we are able to find the solution? That, let us say, if there were 4 matrices and there were 5 ways to compute the matrix multiplication, what do we do? So do we need to perform all the 5 matrix multiplication? So that is basically the brute force solution. So you check out all the parentheses, all the 5 options exhaustively, then see which one is the best. As we did, let us say if there are 3 matrices, there will be 4 ways of doing this. So if there are 4 ways of doing this, in that case we have to compute all the 4 ways and then find out which one is the best solution. So that is called as the brute force. But again, the solution to this particular problem, this is going to be very complex, and the solution to the recursion is, you can say, this is of exponential, and that gives 2 power n. So you can say the brute force algorithm is going to perform poorly if we start increasing the value of n for any value greater than 2. Now, what is the approach? See, if we have to see, we are learning different algorithms with different design strategies, so that we are able to reduce the complexity of the problem. So what do we do? So since brute force algorithm is not good for the case of M, we switch over to the dynamic programming approach. So for dynamic programming approach, what does it say? So it's the structure of an optimal parenthesization. So how we should do the parenthesization? Basically, that will help us in getting us the optimal solution. So let Aij denote the matrix resulting in Ai to Aj. Any parenthesization of this particular matrix must split the product between Ak and Ak plus 1. We know this thing when we have 2 matrices, the 3 matrices, wherever we are going to put the matrices, it is going to split the product. So the cost of number of computing A to K plus the cost of computations which are required for AK plus 1 to J plus this. So as we have done this particular thing, here you can see when we are applying the multiplications, applying the parenthesis, so the cost of multiplying the A cross B, then plus the cost of multiplying the resultant of A cross B, let us say it is M, so M cross C. So we are adding that particular cost, and that gives us the solution, that is the number of multiplications which are required. So the recursive relation, so how do we find out the recursive relation? So repeatedly, how do we perform this particular task? Then let Cij be the cost of multiplication for Ai to up to J matrix, that is the number of scalar multiplications. Then see, because in the dynamic programming, it is a bottom-up approach. So what do? Why we are applying the recursive relations? Because it helps us in getting the previous values. So when we are able to find out the solution to the sub problems, then we can use their results in order to compute the output for the complete problem. So here you see when we are creating, so in the dynamic programming, when we are creating the matrix, so here we say Cij is equal to 0 if I is equal to 0. So that means for a particular matrix, if the value of I is equal to J, then we are going to fill up all the diagonal elements to be 0. Otherwise, what we are going to do, we are going to take the minimum of Cik plus K plus 1J plus di minus 1 d. D over here is representing the dimension. So as I said, so the dimensions are, let us say, if we consider matrix A, so 40 by 20 are the dimensions of this matrix. Then for B, 20 by 60, they are the dimensions of this matrix. So here we are referring B to the dimension of I minus 1. So I is when we are navigating I and J, that means we are moving the row wise and the column wise. So we will be taking the value of that particular dimension, and accordingly we will be moving ahead. So for if I is less than J, only in that particular case, we are going to take the minimum of this. So here we say I and J are referring to the row and column values. Then what is K? K basically Cij, this is the cost of multiplication. So that means in the C matrix, we are going to write the cost of multiplication. So whatever multiplication we perform, whether it is the matrix A with the matrix B or matrix A with the matrix C, here you can see I and J, they are representing the matrix number, whether it is a matrix A, matrix B, or matrix C, first matrix, second matrix, third matrix, like that. And K is representing that is used for finding out for what value of K we are getting the minimum, right? So that means we are going to have two matrices. One is the cost of multiplication, second one is for the K value, which is giving us the minimum value for this multiplication. So that, see, K basically is used over here, but it is going to play a very important role, because K, from the value of K, we are going to decide the point of parenthesization. So whatever is, if let us say the value of K is 3, so that means at third matrix we are going to put the parenthesis. If K is value is 2, so that means for the second matrix we are going to start the parenthesis. So this is how we are going to decide. So the K value plays a very important role. So C is the cost of the matrix. So that means we are going to create a complete matrix for the multiplication cost, and then K matrix, another matrix that we are going to create, that is help us in finding out where to put the parenthesis. Because if we don't know where to put the parenthesis, finding out the cost of multiplication is useless. Now, so computing the optimal cost. If by recursive algorithm exponential time to the power n no better than brute force, then the total number of sub problems is equal to theta n square. So the recursive algorithm will encounter the same sub problem many times. So if the tabling the answers for sub problem, each sub problem is only solved once. So the second hallmark of the dynamic programming is overlapping sub problems, and so that's what you can see, that's the difference between the your recursive algorithm. As we studied, if you remember, we studied about the memorization, and then we also studied about the dynamic programming that we have been studying. So that means, what is the main point, that why it is dynamic programming helps us in finding out the solution? Because when we come across the overlapping sub problems, that means same sub problem coming again and again, then we need not compute that again and again. So we are solving the solution once. So if it we come across the same sub problem again, we are going to use that solution in the future. So that helps us in reducing the complexity of the task. So that is basically the drawback of the recursive approach, that even if we are coming across the same problem again, the computations are done again. They are not using the previous solutions in any way. So where the memorization is being used, that is not there in the recursive approach. So the algorithm says array Ci 1 to n and with Mij, what's the optimal cost for this? Then array K, as I've told you, so array C is being used for recording the optimal cost. So whatever cost is optimal, that the minima of all we are going to store in this particular matrix. Then array K records index K, which achieves the optimal cost when computing Cij. So that means K is going to help us in the parenthesization. So let us say that the input to the algorithm P is equal to P0 up to Pn. Then what the approach, then this particular algorithm, what does it state? So this is the minimum of, we see the for K is equal to 1 to Ji minus 1, we have Q is equal to Mik plus Mk plus 1 comma J plus Pi minus 1. So P, this is, see, the terminology is different, but the formula is same for this particular step that we have done. The cost of the cost matrix, what should be the value on this particular cost matrix? If I is equal to J, then we are going to assign the 0. If I is less than J, then we are going to take the minima of this. So let us do one problem. So this is how, here you say the order of matrix computation. So how are we going to compute the matrix? So we are going to compute the matrix with the minimum difference first. So we see the minimum difference is here. 1 minus 1 is 0, 2 minus 2 is 0, 3 minus 3 is 0. So that means we are going to compute the value of these matrices first, where the difference is minimum. So similarly, then after that, the difference of, see here the difference was 0, and we know here I is equal to J, so we have to just put the values of zeros over here. So first of all, we are going to compute the matrix like this. So next we move on to 1 to 2 minus 1 is 0, 1 minus 1 is 0, 2 minus 2 is 0, 3 minus 3 is 0. So that means we are going to compute the value of zeros over here. So first of all, we are going to compute the matrix like this. So next we move on to 1 to 2, 3. Here you see M1, 2. 2 minus 1 is 1. 3 minus 2 is 1. 4 minus 3 is 1. Then 5 minus 4 is 1. Then 6 minus 5 is 1. So difference is 1. Then we are going to compute the values of these matrices. Then see, here we are saying, see, we are following the dynamic programming approach. We are going to compute the solutions for the sub problems first, and then we are following a particular strategy for finding out the which particular sub problem should be solved first. So here we are taking up the difference of these values. So wherever the minimum is less, sorry, the difference is less, their values are being computed first. So we see then 3 minus 1 is 2, 4 minus 2 is 2, 3 minus 5 minus 3 is 2, 6 minus 4 is 2. So here we have a difference of 2, then we have a difference of 3, then we have a difference of 4, and then we have a difference of 5. So that means in this particular order only the sub problems will be solved, because these sub problems, they are going to be used. So if we are going to follow this particular strategy, in that case the solutions to the sub problems will be used by the solutions to the main problem. So here you can say the first diagonal values in the second one, the second diagonal values in the third one, then in the fourth. So this is how we are moving from the bottom to the top. So this is the way to perform the matrix computations in the dynamic programming and matrix chain multiplication. Then for the parenthesization, as I said, that since 1 to n is computed, Sij is the split position. So from this particular matrix, what is the split position? That is, we are going to use the value of the k, and from there, whatever value of k we are choosing corresponding to the minimum value of the post, that is going to help us where do we have to, where at what point we are going to solve the matrices. So we are going to start from 1 to n. So if I is equal to j, then simply print a, else print bracket, then print optimal parenthesis si comma si minus j, print optimal parenthesis s comma sij plus 1 j. This is how we are going to print the parenthesis when we are going to implement. So as we have already discussed, so in order to get the optimal structure, we have to find out the overlapping subproblems. As we have seen, see these overlapping subproblems, we are going to compute the first where the difference is small, and then we are going to find out the optimal structures, and this is being done using the cut copy paste. That means the solutions which have been obtained for the subproblems, they will be used as it is for finding out the solutions for the optimal structures. So let us now use then try to find out, solve one problem, and then we will go back and see how it is being done. So let us see this particular chain. So here we have considered 4 matrices A1, A2, A3 and A4, and we have, what we have is the dimension of each matrix. Dimension of A1 is 3 by 2, dimension of A2 is 2 by 4, dimension is A3 is 4 by 2, dimension of A4 is 2 by 5. So we have taken dimension, D0 is 3, D1 is 2, as I told you, that is common. So D2 is 4, then D3 is 2 again, then D4 is 5. So we have to remember, because the formula that we are going to use for matrix chain multiplication, it says Cij is equal to minimum of Cik plus k plus 1j plus di minus 1 into dk into dj, right? So, and here we know the value of k, it always lies between I and j, such that k is greater than or equal to I but less than 2. So let us say if I and j are 1, 1. So what will be the value of k? So k is equal to only 1, right? Because it has to be equal to greater than equal to I and less than equal to j. So k is equal to 0 basically. So now we say, because here you can see in the matrix, the first matrix is the Cij and the second matrix is the k matrix, and we have already filled for I is equal to j values. The diagonal elements have already been filled with the 0 values. So now we have to fill up all the other values on the upper hand side. So we are going to do that. So we maintain 2 matrices, as I said. So now we are going to, as I told you, how we are going to compute the matrices. from the minimum difference. If I minus j is equal to 1, because all other zero values we have already computed, so the next difference that comes out to be is equal to 1. So for the difference of 1, what we are going to have? We are going to have 1 2 2 3 sorry 1 1 2 2 3 and 3 4. This is how we are going to compute. They are going to have a difference of 1. So here you see how we are computing. So C12, here you can see C12, this is being computed. How it is being computed? Here you see the formula. At the bottom you see minimum of CIK. CIK, I is equal to 1, K is less than greater than equal to I, as the formula says. K is greater than equal to I, but less than equal to J. J is equal to 2. So K has to be less than that. And it can be equal to 1 also. So K is equal to 1. So that means for K is equal to 1. So here minimum value has to be computed only for K is equal to 1. No other values exist over here. So CIK is C11. So C11 we have taken. What is the value from the matrix C11? It is equal to 0. Then we have plus CK plus 1. K is 1. So it becomes 2, 1. Sorry, J is equal to 2. So it becomes 2, 2. So C22 from the cost matrix, it is also equal to 0. Then the third part comes di minus 1. So I value of I is equal to 1. So 1 minus 1 is 0. So dimension d0 is 3. So we have taken 3 from here. Then dk, k is equal to 1. So dimension d1, this is equal to 2. So we have taken 2. Then dj, j is equal to 2. So we have taken the d2, that's value is equal to 4. So that gives us 3 multiplied by 2 multiplied by 4. That gives us 0 plus 24. The final answer for this is 24. So the value of C12 is equal to 24. This is how we are going to compute. So for the difference of 1. So the next value we compute is 2, 3, as I said. So 2, 3, here you see the value of CIK. See, I'm just following the formula only. CIK, I is equal to 2, 3 is going to be, K is equal to 2 only. So for C22, here we get similarly K plus 1. 2 plus 1 is 3. So J is already 3. So we get 3, 3, 3. Then DI minus 1. I is 2. So DI minus 1 is 1. So D1 is equal to 2. Then DK. K is equal to 2. So we take the value of D2, that is equal to 4. And then we are going to DJ. J is equal to 3. So the value of D3 is equal to 2. So again we get 4 multiplied by 4 is 16, because C22 and C33, their values are, their diagonal elements, their values are 0. So we get the final value as 16, and we have filled up the cost matrix with this particular value. Now similarly, we compute the value of 3, 4. So here we get 3, 4. So from again applying the formula C33, these values become 0, and the other values we are getting 4 by 2 by 5. So when we multiply this, we get the value of 40. So we are able to fill this particular, you can say the diagonal of this particular matrix with the values. The difference between the I and the J value is 1. Now we move on to the next layer. The difference between the I and J values are equal to 2. So that means we are going to compute the value of 1, 3, and we are going to compute the value of 2, 4. 3 minus 1 is 2, 4 minus 2 is 2. So there we are going to get the 2, 2 values for K. So here you can see if we compute the value of 3 and we again apply the formula. So because the value of K, this is less than equal to, greater than equal to I and less than equal to J. So where we see, for we are going, since the difference is 2, we are going to have 2 values, K is equal to 1 as well as K is 2, because 2 is also less than 3. So we have to do the computations for 2 values of K. So here you can see K is equal to 1, comma, K is equal to 2. So from here, so we have applied the same formula for K is equal to 1, and similarly for K is 2. So see over here, one thing that I forgot to tell you, see the values where we are, see, along with the cost matrix, we are also filling the K matrix. So the 24 value we got where value of K is equal to 1. Therefore, in the K matrix, we have filled value of K is equal to same position, C12. C12 in the K matrix, we have filled the value of K is equal to 1. k is equal to 1. Similarly, for in the case for 2, 3, we have filled the value of k is equal to 2. Similarly, for the 3, 4, we have filled the value for which we have done the computations k is equal to 3. So we are filling the k matrix that is basically going to be used for the parenthesization that the next values. Now we see when we perform this particular computation for k is equal to 1 as well as for k is equal to 2, applying the same formula, we get 16 plus 20 12 is 8 and the other value is 48. So that means for k is equal to 1, the value is 28. For k is equal to 2, the value is equal to 48. And the minimum of these is 28, and 28 we are getting the value for k is equal to 1. So that's why in the C13 we have cost matrix value is 28, and for what value of k we have obtained this value of 28, we have written over here k is equal to 1. So this is how we are going to fill the next value also. So this you should do as an exercise, and the finally that we get that in the cost matrix the minimum value that we are getting is 36, and this value we are able to get for k is equal to 3. So similarly we are going to see we have to fill just one upper triangular matrix. We are not going to compute the lower triangular matrix because that is not required. So similarly when we do this particular task for C14, so we have to do here you can see this is a complete tree. Now when we will do this particular task, we will come across C. So we have k is equal to 1, we have k is equal to 2, and we have k is equal to 3. And from there we can we need not perform all the computations. We have certain results already with us. Like C11 is 0, C24 let me see the table. So C24 already computed. So from here C24 is already computed. So we will see why we have followed this particular path. All the solutions to this particular problem, they have already been computed. C12 is already computed. C34 is already computed. C13 is already computed. Then C44 is 0. So the many of the computations have already been done, and we need not redo all the computations. And we are just going to put these values in this particular matrix. So after performing all the computations, we get C14 is equal to 58. That means for multiplying all the matrices from 1 to 4, the minimum cost that we can you can say for the multiplication of all the 4 matrices, we can perform the multiplication with the best cost, or you can say the minimum cost of 58. Now we know this is 58, but where to put the matrices? Okay, so the main problem is where to put the parentheses. So for the 4 values, see for 1 to 4 we have value of 58. For the same position what we have, the k value is 3. So that means we have to put the parentheses at third position. So the corresponding to this 58 using the cost matrix, parenthesization using the k matrix, from 1 to 4 what is use parenthesis at 3. So what we have done, a cross 2, a cross 3, right? So we are putting the parenthesis and filling the a for aside. So that means this is the first level of parenthesis that we have done. Now we have a1 to a3. So from 1 to 3, right, where to put the parenthesis? So here at 3 what we see, the parenthesis value is 1. So we will put the parenthesis over here at 1. So that means first we will perform the matrix multiplication a2 cross a3, and then what we are going to do, then we are going to multiply this the result of a2 a3 with the a1, and then the result of all these three will be multiplied with the a4. Then we are going to perform the minimum with this particular sequence of matrix multiplications is going to be performed with the minimum cost of 58 multiplications. So this is how we solve the problem of matrix chain multiplication using the dynamic programming approach. So the number of overall sub-problems into the number of choices, that is equivalent to on square into on, that is equal to on cube. So the cost of solving the sub-problems plus the cost of making the choice, that is cost of choice, is di minus 1 into dk into dj. So this is the running time for the matrix chain multiplication. So that's all for the today.